Today we're going to be doing a problem that was recommended to me by one of the students taking this class. Amazing problem. I was unable to solve it with the class today, but after some pondering and some checking of the solution manual, we're going to slam it in this video today. Hopefully you guys learned something interesting, and hopefully this problem is beneficial. This is a review problem of Chapter 2, Serway and Jewett, Physics for Scientists and Engineers. I have the 9th edition. This is problem 82. You can find other editions. The problem should be there, maybe just under a different number. So we're going to read out the problem. As soon as a traffic light turns green, a car speeds up from rest to 50 miles per hour with a constant acceleration of 9 miles per hour per second. In the adjoining bicycle lane, a cyclist speeds up from rest to 20 miles per hour with a constant acceleration of 13 miles per hour per second. Each vehicle maintains constant velocity after reaching its cruising speed. A, for what time interval is the bicycle ahead of the car? B, by what maximum distance does the bicycle lead the car? So first thing we want to do is probably draw a picture. A picture would be pretty nice. We have a car, which I'm going to draw here as so. The car starts at rest, 0 miles per hour. We're going to keep it with the mile units. And then it accelerates with an acceleration equal to 9.00 miles per hour per second. And then it reaches a final cruising speed at 50 miles per hour. Next to it is a bike, which starts also at initial velocity. It has a different acceleration. Its acceleration is a little faster than the car at 13 miles per hour per second. And then it reaches a slower cruising speed of 20 miles per hour. Each vehicle maintains constant velocity after reaching its cruising speed. For what time interval is the bicycle ahead of the car? When the car and bicycle start moving, the bicycle is accelerating faster than the car, so it's going to overtake the car. But eventually, the car accelerates to 50 miles per hour, so it's going faster than the bike after they reach their cruising speed. So eventually, the car is going to overtake the bike. The moment the car overtakes the bike, they're going to be at the same position. At that position, if we find the time, that is how long the bike will be overtaking the car for. So first thing I kind of had an idea of doing was figuring out what is the time at which both of these vehicles stop accelerating. So the way we can do that is by breaking everything up into the respective sections for car and for bike, and asking ourselves, what is the initial velocity, final velocity, acceleration, and time? So this equation should spring up. Final velocity is equal to initial velocity plus the acceleration over some given time step. We're looking for the time. For the car, we know the car reaches 50 miles per hour. Its initial velocity is 0 miles per hour. It is accelerating at 9 miles per hour per second, and here we need to find the time. So how do we find the time? We could just do 50 miles per hour divided by 9 miles per hour per second. This gives us the time. Check out how these units cancel out. So we have miles per hour, and we are dividing this by miles per hour per second. So if we flip this whole thing, we get miles per hour times seconds miles per hour. So this miles per hour cancels with this miles per hour. And the final unit we have here is seconds. These are the only units that don't get canceled. So basically what we have is 50 divided by 9 seconds. Let me pull up my phone calculator here. 50 over 9. We have 5.55. Is that facts? I feel like it's not. 5.55 seconds. We could do the same thing for the bike. So the bike reaches its final velocity at 20 miles per hour. Its initial is 0 miles per hour, and it is accelerating at 13 miles per hour per second for a specific time interval. We already know this time interval is in units of seconds, and we can just do 20 miles per hour over 13 miles per hour per second. So this gives us 20 over 13, which is 1.54 seconds. Interesting. So what is happening here is the following. It's probably good to draw a little graph to see how things are moving. So here we have time, and here we have the velocity as a function of time. I'm going to do the car in red. So the car starts with a smaller acceleration, so its slope is smaller, and then it reaches a final value over here where its velocity is constant. This final value, you can draw a line all the way to the velocity. This will be 50 miles per hour. This is for the car. And the slope at this part, slope is equal to 9 miles per hour per second. The slope of a velocity time graph is the acceleration. Now we also have the bike, which is accelerating for a shorter amount of time, but at a higher rate. So maybe it accelerates like this, and then it's flat. This is the bike. And the value that it stops accelerating at here is 20 miles per hour. Again, its slope 13 miles per hour per second. So what's happening here? The bike is accelerating. Right here, it hits 1.54 seconds, which we calculated with this equation over here. The car accelerates at a slower rate, but for a longer time, 5.55 seconds. The car reaches this final velocity, 50 miles per hour, and then it coasts forever. The bike reaches its final velocity, 20, and it coasts forever. The point where they are at the same position is where we want to find their time. How long does it take for the car to overtake the bike? How do we do this? Well, here, it would be interesting to find how much distance the bike has traveled after it has accelerated, and the distance the car has traveled after it has accelerated for its amount of time. So if you have a particle under constant acceleration, its position looks like this. Initial position plus initial velocity times however long this particle is traveling for, plus 1/2 its acceleration and the time squared. For the bike, we know that it accelerates for 1.54 seconds. So we have this value. We know that its initial velocity is 0 meters per second. And we also know that its initial position is 0 miles. Sorry, I said meters. It should be miles everywhere, because we're working with miles. So now we can plug everything into this final equation. We have 0 miles initially plus 0 miles per second initial velocity times 1.54 seconds. Doesn't really matter. Things get canceled here. Plus 1/2. Its acceleration is 13 miles per hour per second. And we multiply this by 1.54 seconds squared. So what we have here is this thing is 0, this thing is 0. The only part of interest is right here. So let's see what that looks like. I'm just going to multiply all these numbers together. So I have 5 times 5, 5 squared. Or, my bad, 1.54 times 1.54. This is the time squared. Times 13 acceleration times 0.5, which is the 1/2. So we have 15.4154. But watch out for the units here. What we have is miles per hour per second times seconds squared. And here, one of these seconds cancels with one of these. So the final units over here look like they are miles per hour times seconds. If we want to cancel this hour and this second to get a final position in units of miles, we have to do an extra step here. So miles per hour times seconds times what can we multiply such that the hours get converted to seconds? I can put 1 hour at the top here and 3,600 seconds. in this case, what happens is this seconds cancels with this seconds, this hour cancels with this hour. So we just take our number and divide it by 3,600, and we should get the final result in miles. Is that okay with you guys? So we have position final is equal to 15.4154 divided by 3,600. We get 0.00428 miles. So this is the distance that the bike has traveled. Bike distance after 1.54 seconds of acceleration. After that, it coasts at a constant velocity of 20 miles per hour. Let's find the same position for the car. So why are we doing this? Well, if we find the final position of the car, it will kind of give us an estimate of when they coincide in position. So here we have X final for the car. It's originally at 0 miles per hour. Then we have 0 miles per hour times time. In this case, we can plug in this 1.54 seconds. And the equation I'm using here is this one. X initial plus V initial times time plus 1/2 AT squared. Important kinematics equation from the model that checks particles under constant acceleration. So now that we have this, we can also add here the acceleration of the car, which is 9 miles per hour per second times 1.54 seconds, and this whole time thing is squared. So again, the original things here that are in 0 cancel out. All we have left is this final part, which will give us a position. And what this looks like is 0.5 times 9 times 1.54 times 1.54 divided by 3,600 to convert this in miles. We get 0.0029645 miles. So this is car after 1.54 seconds acceleration. So what have we done here? Let's draw a little graph of the position as a function of time. What color did I use for the car? I used red. So the car's position after accelerating, like it is accelerating, so its position is increasing like crazy. And the bike is actually accelerating a bit faster. We used blue for the bike. The bike is accelerating here. It reaches this value and then it goes with a constant velocity. The car accelerates for probably a bit more and then it goes like this. So what we just looked at is this time interval right over here at t is equal to 1.54 seconds. This is exactly where the bike stops accelerating bike. Then it reaches constant velocity. And actually, it would probably be cool to write the slope over here. Slope is 20 miles per hour. And the slope here is the acceleration, which is 13 miles per hour per second. So an accelerating particle, its position versus time plot looks kind of like an exponential, like a parabola sort of. And a constant velocity looks just like a straight line. So we can see that the position of the bike is at 0.00428. This number is bigger than this number. So that is why I drew that here. So this would be the position of the bike, which is exactly this number here. That number would be right over here. And this number would be the position of the car over here. Why is this important? Well, we can see that after the bike has fully accelerated for those 1.54 seconds, it is still ahead of the car, right? Its position value is higher than the car's. So the car has to continue accelerating for a little bit as the bike is coasting at its 20 miles per hour. So when the bike coasts for a while, you could see this intersection point. I don't know if this is when the car is still accelerating. Probably is. We're not sure, but you could see the intersection point right here. This is the value in time we have to find where their positions are equal. So this is very important. The positions here of the car and bike are equal. And when they're equal is when we are looking for this time step. This time step to answer part A. What time interval is the bike ahead of the car? After their positions are equal, they are at the same place for just a moment in time, but the car has a greater velocity. It is going at 50 miles per hour. So eventually the car is going to overtake the bike. But originally, since the bike has greater acceleration, it is overtaking the car for just a small period of time. So let's find this position in time as a function. So what we have is the bike final position. Actually, the bike's final position. Let me do bike final and then bike over here at 1.54 seconds. What this equals is this 0.00428 miles. And then after this, the bike is going at constant velocity. So its function of time is going to be equal to its initial velocity, its initial position, plus its constant velocity times time. This is the straight line function that I have represented right over here, right? The slope is 20 miles per hour. That is our V. The time is just the time axis over here. And the position is just increasing as a straight line. The position is increasing as a straight line. This is y equals mx plus b. And this b is the initial position right over here. So let's take a look at how we can work with this. We have a final position of the bike as a function of time, and it starts at 0.00428 plus 20 miles per hour. But the important thing here, this time, is we are starting this function over here. We're starting this function at a time interval slightly after here. So we should kind of imagine that the axis has changed a little bit and that we are starting right here. So all of this time that has passed, this 1.54 seconds, is kind of gone. I think the way you can do this is you have time minus 1.54 seconds. So if you plot this function here, it's going to straight up look like only this. And then if you plot this function over here for the bike, which looks like this, except instead of having this time over here, this 1.54, you just have the letter T. That will show you the plot over here. So now we have this. What we should find is the function for the car as is going here. And if we equate those two, if we equate the position of the bike as a function of time and the position of a car as a function of time, what we're doing is basically saying we want to find this exact location. This is where x of the bike equals x of the car. And here, if we look down and find this t value will be the answer for part A. I hope that makes sense. Luckily enough, we have the equation for the position of a car. It is exactly what we saw before. So initial position is 0, initial velocity is 0. So we just have 1/2 and then its acceleration, which is 9 miles per hour per second. And here we have a time. We're going to leave the time blank because that's what we're looking for. Now what we can do is equate this with this, and we're going to have an equation for time right here and right here. Oh, my mistake, there's a t squared over here. Then we can solve this equation. So let's bring up the white color here. This is going to be 1/2 times 9 miles per hour per second times t squared. This is equal to 0.00428 miles plus 20 miles per hour. This is being multiplied by the time, and then you remove this little portion where the bike is not moving with constant velocity. Amazing. What can we do here? Well, I think we should move things to one side, right? Let's see. So first thing I'll simplify is just remove the units from here on out. We have 4.5, 9 times 1/2 is 4.5, t squared. This is equals 0.00428 plus, we have 20t, and then minus 1.54 times 20. 1.54 times 20 gives us 30.8. But this is the annoying thing, because what we have here is in miles. This is the only number in the equation that doesn't have a t in front of it. And this number is in units of miles. But this number is not in units of miles. It's actually in units of miles per hour times seconds. So the way we converted this before was we just divided by 3600. And here what we get is 0.00856. Now this has units of miles. And we can combine these two. So what I'm going to do is 0.00428 minus 0.00856. Now we can rewrite this equation with everything on one side. Let's move all of our values so they are on one side. So here we have positive 0.00428. We have minus 20t plus 4.5 t squared. Let's actually plot this. All right, guys, actually one other mistake here. You could see I've changed the equation a bit. Why this happened was because here we had miles per hour per second, right? Here we have miles. Here we have miles per hour. What I figured out we have to do is divide everything here that has miles per hour by 3600. So this number here was correct. This is in units of miles. We did that by adding these two things up in miles. Then this number here, 20, actually comes from 20 miles per hour. I divided this by 3600 so that here we have miles per second. The units work out because what we're looking for here is time in seconds. So if we multiply 20 miles per hour by a unit in seconds, this doesn't make sense. We're going to get our value in like hours or something like this. So I divided this by 3600. Sorry, divided this by 3600. I got this number. Same thing here. This 4.5 is 9 miles per hour per second. But what we have here is it's being multiplied by t squared, and we want t to be in seconds. So I divided this 9, or this 4.5 by 3600. This cancels out the hours and converts everything to seconds. That is this number here. And this is a quadratic equation. If you want, you can use the quadratic equation, or you can just plot this in Desmos, and you're going to find the roots over here. There's two roots because quadratic functions have two places where they hit 0 most of the time. And this value at 1 second doesn't make sense because this happens before the bike has fully finished accelerating. Remember, we found out the bike accelerated until 1.54 seconds, and we found out that the position where they intersect, the last moment in time where the bike is overtaking the car, happens after this. So the only possible answer could be the other route, which is 3.45 or 3.46. Let's put t is equal to 3.45 seconds. Put this in a box, and this is the answer for part A. I checked the solutions in the book, and they're not the best. They convert everything to feet per second, but the final answer they get is 3.45 seconds for part A. So this is the answer. In summary, what did we do? First, we found out how long each of the vehicles accelerates for, because they reach a final velocity. So they've only accelerated for a specific amount of time, and then they coast. Then I plotted this just to show you guys what it looks like. So the bike accelerates at a greater slope than the car, but it accelerates for less amount of time. So the time that the bike accelerates for, we saw was 1.54 seconds, pretty important. And the time the car accelerates for is 5.55 seconds. This 5.55 is not too important, but it's pretty useful if you're creating a plot. The next thing is I want to find what the positions of the objects, the car and the bike, were at t is equal to 1.54 seconds. So after the bike finishes accelerating, I found its position using this equation, model for particle under constant acceleration, and I saw that the bike has reached this value in miles. Then I was curious where the car is, so I used the same equation for the car. I plugged in 1.54 to see where the car is at the moment in time the bike stops accelerating. So we see that it is this position, and this number here is smaller than this number here. So we can see that at this moment in time, after the bike has stopped accelerating, the bike is still ahead of the car. Then I was like, all right, let us draw this graph here, which shows the bike accelerating until it reaches its maximum value at 1.54 seconds. We already know what this maximum value is. We found it over here. And then after that, it proceeds to go at a constant velocity of 20 miles per hour, which is a constant slope on the position time plot. So this is what the bike is doing. Boom, boom. I actually tried plotting this stuff in GeoGebra and it didn't work, probably because of something going on with the units. But you can imagine something like this is happening for the bike and something like this is happening for the car. Just test it out. And then what we did was create a function for the position of the bike. We did this using the particle under constant velocity, and we took into account that this car only enters constant velocity after 1.54 seconds. So from the time, it's like I remove this for this plot to work, right? Because I'm shifting this function from originally it being over here to now it's starting over here. Then I pulled in the position as a function of time for the car, which is still under constant acceleration. So the initial position and initial velocity are 0. And then we equate the two, make sure the units work out by dividing by 3600 in certain locations, and then solve the quadratic equation, and we get this over here. Now let's check out part B of this problem. It says, by what maximum distance does the bicycle lead the car? So we need to find a maximum distance, and we already know that the bike is faster than the car initially. So at some point, the bike is going to reach its maximum velocity, and the car is going to continue speeding up because the car reaches 50 miles per hour. At the point where the car's velocity and the bike's velocity are the same, just after that moment in time, the car is going to continue accelerating and surpass the bike in velocity. So the bike is going to speed up. It's going to reach a further and further lead ahead of the car until the car matches the bike's velocity. And then that lead is going to shrink and shrink and shrink until the car and bike are at the same location, which we found in part A. So we see that the velocities have to be the same, and in that moment in time, the gap is going to get smaller. So what this piece of information is telling us for part B, the V of the bike has to equal the V of the car. The maximum velocity that the bike can reach is 20 miles per hour. And the car is going to exceed 20 miles and is going to reach 50. When the car reaches 20 miles per hour, the very next instant in time, it's going to go a little bit faster and it's going to start gaining distance onto the bike. So we need to find at what point in time does the car's velocity also equal 20 miles per hour. So we know that the equation, we know that one of the equations for particle under constant acceleration looks as follows. The final velocity is equal to the initial velocity plus the acceleration times time. We know that the initial velocity for the car is 0, so we can get rid of that. And we want to find at what moment in time does the car reach 20 miles per hour. So this equals the car's acceleration, which is 9 miles per hour per second, times time. If we divide 20 miles per hour by 9 miles per hour per second, all the units cancel and what we're left with is seconds. So pulling up the calculator, we have 20 divided by 9. This gives us 2.22 seconds. So at this moment in time, car starts closing the gap. And at this moment in time, the bike has the biggest lead on the car that it's ever possibly going to get. Every following moment in time, the bike is going to get closer and closer to the car, or the car is going to get closer and closer to the bike. So what we can do is find the position of the bike at this moment in time and the position of the car at this moment in time. Let's find the position of the car first, because I think it's easier. The position of car at 2.22 seconds is equal to the car's initial position, which is 0, plus the car's initial velocity, which is 0 times time, plus 1/2 the car's acceleration, which is 9 miles per hour per second, times 2.22 seconds. And these are squared. So what we have here is 0 plus 0.5 times 9 times 2.22 times 2.22, and we divide this whole thing by 3600 to cancel out those hours in the mile per hour per second. Everything left is in seconds, so the seconds cancel. So our final answer here is going to be in miles, and what we have is 0.00616 miles, the position of the car. Now if we find the position of the bike at this location in time, so we already saw the position that the bike will be at after it has finished accelerating. So after 1.54 seconds, the bike has finished accelerating and has reached this position. So I'm just going to copy this position right here. Copy. And put that right over here. And this is going to be at 1.54 seconds. So we want to find the bike's position at 2.22 seconds. If we subtract 2.22 and 1.54 seconds, what we get is 2.22 minus 1.54. We have 0.68 seconds left for the bike to just constantly cruise at its constant velocity. So the position that the bike will reach at this time, if we say its initial position after the constant velocity is 0, or after it reaches constant velocity, we will put its constant velocity, which is 20 miles per hour, times this 0.68 seconds that it has passed. So what we have here is 20 times 0.68. Divide that by 3600 to cancel out those hours and turn them into seconds. And what we get is 0.00377 miles. So the bike has traveled this much after it has finished accelerating for that 1.54 seconds, after which it's going to cruise at a constant 20 miles per hour for just a little bit longer until it reaches this moment of interest, 2.22 seconds. So the final position of the bike is going to be 0.00428 plus 0.00377. So we reach 0.00805 miles. This is the final position of the bike. Now that we have the final position of the bike and the final position of the car, we could just see what that gap is. So obviously the bike is further, it has a lead. If we take the position of the bike minus the position of the car, we can see that this is 0.00805 minus 0.00616. This is 0.00189 miles. And the book actually has the answer in feet. So I'm just going to check miles to feet conversion. 1 mile equals 528 feet. We have here 0.00189 miles. and this is roughly 9.979 feet. And the book rounds this to 10 feet. And this is the right answer. So, crazy problem. How much time does the bike lead the car by? And at the fastest or at the largest gap between the bike and the car, what is that distance? That is 10 feet. I'm not going to go through this anymore. The video is already quite long, but try this problem out on your own. Try to kind of argue your way through this. Like I said, I was not able to solve this problem the first go, but I think that's pretty valuable. You guys should try doing this. Don't just check the solution manual. Try to hammer home every single piece of logic that you have in your head, and you will get comfortable with all these equations. By the way, I said in the beginning of the video, this is a review problem. Very cool review problem, because we saw that this problem uses constant acceleration and constant velocity equations, which is pretty much everything in chapter 2. By the way, the chapter 2 summary video is coming out soon. Let me know if you guys want to see any specific videos, and I'll try to slam them on this channel. Thank you guys as always for watching. See you in the next video.